Welcome to week number 3 of ECE 401 Senior Design 1. In this lecture, we're going to look at breadboards, Raspberry Pi Picos, and a programming language called Python. Now, if you go to Bison Academy under Senior Design 1, you'll see the next couple lectures. The prereq for Senior Design is Circuits 1. So we really can't guarantee you have any background on electronics, Circuits 2, embedded systems when you take this course. Some of that information you need because what we want to do at the end of the semester is have a working device like this, a stoplight. So we're going to be doing kind of a quick overview of those courses over the next 3 weeks. Today is Breadboards and Raspberry Pi Pico, basically embedded systems, how to wire up a microprocessor, how to program it to make a light blink. On following week, we'll look at Circuit Lab and op-amps, review of Circuits 1, Circuits 2, and then diodes and transistors, review of electronics, stuff you're going to need to build one of these devices. So let's start out with breadboards and Raspberry Pi Pico. Now in Senior Design 1, it's your choice. You can use a microcontroller if you want. You cannot use a microcontroller if you want. The microcontrollers can really simplify quite a few designs. They provide a great deal of flexibility. They make changing your design as simple as downloading a new program. It's your choice though. If you do use a microcontroller, use a Raspberry Pi Pico. They're only $4. If you don't use a microcontroller, then you don't really need this lecture. However, when you get to Design 2, Design 3, almost all designs use a microprocessor. The Raspberry Pi Pico is really, really powerful. To illustrate that, let's go back to Bison Academy. If I go back to Advanced Embedded, this is the course where we cover the Raspberry Pi Pico. Again, very few people in Senior Design have had Advanced Embedded, but this is a resource. This kind of covers some of the things you can do with the Raspberry Pi Pico. Go under Best of 476, and it kind of shows off some of the things you can do. For example, with a Raspberry Pi Pico, I have access to GPS sensors. With that, for example, this is using a Raspberry Pi Pico along with a GPS sensor. This is my latitude and longitude. So when you find something you want to remember where it was, like where's my cat, I can click a button and it tells me where I am relative to my cat. As I walk around, I can see my distance to the cat changing. Shows up on the display. And if I want to go back and find my cat, just turn around and go back to 0, position, and voila, there's your cat. With Raspberry Pi Picos, I have access to sensors. For example, I can have an air pressure sensor, tell you the air pressure at the basement of Ag Hill. Climb the stairs, I can then tell you what the air pressure is at the top of Ag Hill, and from the pressure drop, tell you the height of the building. So going up the stairs, here's the pressure. It's dropped by 3.7 H-pascals. That'll tell you the height of the building. In addition, with the Raspberry Pi Pico, you have access to Bluetooth and Wi-Fi. Here, for example, is a Bluetooth interface. I can talk to the Raspberry Pi Pico using Bluetooth. So when I connect, I can send commands and change the brightness of an LED. I can also do that using a Wi-Fi interface using tags, connecting up as a wireless network or connect as a client. Basically, the Raspberry Pi Pico is extremely powerful and solves a lot of problems you're going to run into in Senior Design 2, Senior Design 3. So in preparation for Design 2 and Design 3, we recommend, or actually require, that if you do use a microcontroller, use a Raspberry Pi Pico. It's actually very, very friendly. And they're cheap, $4. But it's your choice. You don't have to use a microcontroller if you don't want in Senior Design 1. It is pretty useful though. I'd recommend it. In this lecture, we're going to be covering breadboards, what they are, some do's and don'ts in breadboard design, hardware, how to wire up a Raspberry Pi Pico on a breadboard, connect a push button to it, a speaker, and an LED, So you can turn the LED on and off when you hit a button, or play a tune when you hit a button. And software, writing programs using a programming language called Python. Now, Python is very similar to MATLAB. If you're familiar with MATLAB, you basically know Python. We'll also look at how to set up your Pi Pico so it executes a program on power on. So that's today's hot topics. Starting out with breadboards. Once you have your circuit, you've designed it on paper, you've tested in simulation, it's time to start transferring your circuit to a breadboard. Now, breadboards are an easy way to build your circuit and check your design to make sure it works in practice. Most of the breadboards used in ECE are 830 type breadboards. These have 4 edge connectors that are shorted along the length. Those are these guys right here, the red, blue, red, blue. These are typically used for power and ground, so oftentimes I'll set this up as plus 5 volts for red, this being ground. And likewise over here, another plus 5 and ground. So all these along the whole line is ground. All this along this strip is 5 volts. If you peel off the back, which you don't recommend because it ruins the board, but if you do peel off the back, you can see this kind of short. This is a big shorting bar. Everything along these lines are shorted together. In the middle, you've got these are shorted left to right. The idea is I'm going to place an IC, say right here, and I now have 4 different pins to connect to pin 1. These 4 pins connect to pin 2, and so on. For example, the following breadboard circuit uses 5 volts for the top trace, ground for the blue line, another 5 volts and ground. These connect to 2 ICs. Pin 1, for example, in this IC is all along this line. Here's pin 2, pin 3, pin 4. And then the circuit is connecting components to each of the pins and going between them. That's kind of what a breadboard circuit looks like. The purpose of breadboarding is to verify that your design works in practice. So the first 2 steps you should have done already. That's your paper design, step 1, simulation for step 2. Now with the breadboard, I'm going to check to see, does it work in practice? Once it works, I'll transfer my design to a PCB. That's more permanent and abuse tolerant than a breadboard, less noise sensitive, smaller, easier to package. But the problem with the PCB is it's kind of hard to modify. For example, here's a PCB. If I decide this resistor actually ought to be a different value, well, that's a problem. I've got to desolder it, solder a new one. If this is going to the wrong pin, that's a bigger problem. I want to get the design correct before I go to a PCB. That's what a breadboard is for. There's a couple tricks in laying out your circuit board on a breadboard. The first trick is keep your circuit neat. If you have a jumble of wires like this, it's really hard telling which wire's in the wrong spot. Are the chips connected? Does each one have power and ground? Basically, if you have a circuit like this, typically, when you come in for help, this will say, rip it up, do it again, only now keep it neat. By keeping it neat, that means keep the wires short, cut the resistors so they just fit right next to the breadboard. That keeps the noise level down. All these wires down here are antennas. They pick up radio signals. Keeping them short keeps the noise level down. It also makes it easier to see where everything's going on the board. Now, this does cost some money. The resistors are about 2 cents each. When you cut the wires short, you're going to probably throw out the resistor when you're done. We don't care about 2 cents. Go ahead and waste the 2 cents. Second trick, color code your wires. Use red for 5 volts, black for ground, different colors for different signals. For example, in the top circuit, I can see each chip has got power, each one has ground, I've got the signals coming on. If there's something wrong, I can kind of see what's happening. The bottom circuit, however, I've got random colors going everywhere. It's really hard telling what's going on. If something's wrong with the circuit, good luck trying to find it. So color code your wires. That's why they have different colors of wires. Third trick, use potentiometers. For example, if I want this to be 1 second on, 1 second off, I can calculate what R1 and R2 should be. It might be a little bit wrong. What a potentiometer does is this is a variable resistor. I can adjust the resistance to get the on time to precisely 1 second. I can adjust the off time to precisely 1 second. That's what R1 and R2 do as a potentiometer. A potentiometer is a resistor that has a center tap. I can use this as a variable voltage or a variable resistance. If I do it this way, 5 volts on one side, ground on the other, the center tap can pick up any voltage between 0 and 5. I can use it as a potentiometer. If this is, say, a 100K potentiometer, when the wiper is over here, the total resistance is 100K. If it's in the middle, I've shorted out half of it. It's now 50K. All the way over here, it's now 0K. That makes a variable resistor. So using potentiometers helps you adjust your circuit, tune it once it's built on the PCB. So potentiometers are useful. However, they're also expensive. A resistor is 2 cents. A potentiometer is $1.55. So don't use hundreds of them. You're allowed to use 2 potentiometers on your design if you want. You don't have to, but they can save headaches later on. For example, if I have a comparator, that's this circuit, that's something we'll cover next week. What this does is this outputs 0 volts or 5 volts. If this is a 2 volt reference, whenever the VA is more than 2 volts, the output is 5 volts. When it's less than 2 volts, it is 0 volts. That's a comparator. So it kind of has this type of relationship. And the on-off voltage is what this guy is. The voltage corresponds to a light level. As the light level changes, VA changes. When VA is bigger than 2 volts, I output 5 volts, otherwise I output 0. Well, if I want this to be something specific, like at 100 lux, depending on the light sensor, the voltage may or may not be 2 volts. What the potentiometer does is it lets me adjust this up and down, so I can adjust the voltage so it turns on at 100 lux, whatever that voltage is. That makes it easier because I don't have to replace the resistor, replace the voltage. Once I build the circuit, I can adjust it based upon the actual value of the sensor, based upon the actual light levels. That's a potentiometer. Third trick is use test points. Some things to think about when you're using a breadboard are, how do you test your circuit? How do you know that it works? What signals do you want to look at? What should the signals look like? What procedures do you use to make sure your circuit is working? Note that when your signals, note what signals you look at and you record when you try to verify that your circuit works. Those signals that you look at are signals you're going to need when you get to the PCB. Those are your test points. And a good way to check to see your circuit works is record the signals on your breadboard, record them on your PCB. The signals should be the same. If they're different, then you know something's different between your breadboard and your PCB. Kind of probe it and try to find out what's wrong, what's different. Example is, here's a circuit. This is a comparator or Schmitt trigger that drives an LED through a transistor switch. The signals that I'm probably going to want to look at to make sure this works is I'm going to want to know power and ground. If I don't have power, it's not going to work. If this is a light sensor, I want to know what is the voltage coming out of the light sensor. What is the voltage I'm comparing it to? What is the output of the comparator? This should be 0 volts or 5 volts for a switch. Is the transistor saturated? This should be 0.2 volts when saturated, 5 volts when turned off. What's the current through the LED? To do that, I'll measure the current through the resistor. To measure the current, I'll measure the voltage across the resistor. Then from V equals IR, I can calculate current. So those are things that I want to measure. Things that you'll measure on your breadboard, and when you get your PCB, these will be the test points I want to have available on my PCB. Finally, with the breadboard, keep your breadboard. When you're done testing your breadboard, keep it intact, meaning don't cannibalize parts. That's kind of your gold standard. When I solder up a PCB, if it doesn't work, I can compare the signals to the working breadboard and see what's different. Once the PCB works, I can then cannibalize it and use the parts to build a second PCB. What that means is you need 2 of every part in ECE 401. You're going to need 2 anyway because you want to have 1 working circuit for each person. So that's kind of the idea behind breadboards. The second thing to look at today are breadboarding with a Raspberry Pi Pico. For example, here's a little breadboard with a Raspberry Pi Pico. It's got the Pico on the breadboard. I've color-coded it. These are the ground lines. Power is actually supplied by the USB port. It's got buttons, an LED, and a speaker connected to it. Now, on the Raspberry Pi Pico, the basic connections you need for power and ground are as follows. I need ground. Any of these pins work for ground. They're all shorted together. For power, I've got three different options. If I connect to a USB cord, like I have right here, I've got power coming from the USB. I can power it using 5 volts, like you'll do in your final design. That goes to BSIS, pin 39. That could be anything between 1.8 and 5.5 volts to power your Pico. B-bus is the 5 volts out if you power through the USB. And 3B3 is 3.3 volts out. The Raspberry Pi Pico actually runs on 3.3 volts. If you want 3.3 volts for the rest of your circuit, that's available, and this is capable of driving up to 300 milliamps. Yes, 300 milliamps. Now for the microprocessor, I can have binary inputs and outputs or analog inputs and outputs. In 401, we're just using binary. For binary I/O, that could be any one of pins GP0 to GP28. For binary inputs, the Pico runs at 3.3 volts. 0 volts is logic 0, 3.3 volts is logic 1. And each I/O pin can source or sink up to 12 milliamps. For binary inputs, 0 to 0.8 volts is logic 0, 2 to 3.5 volts is logic 1. As a note, you are not supposed to apply 5 volts as logic 1 to a Pi Pico. The Pico can actually sort of handle it. In all the chat rooms, when people talk about I'm using 5 volts as the input, there's usually somebody from the Raspberry Pi Foundation saying, please don't. It's rated at 3.5 volts. It is not rated at 5 volts. The users kind of say that it seems to work fine at 5 volts. No guarantees, though. If you try that with a Raspberry Pi, 5 volts will kill your Raspberry Pi. So you're not supposed to apply anything more than 3.5 volts to a Pi Pico. Example of a schematic. Suppose I want to have 2 push buttons connected to my Pi Pico, a red LED, and a speaker. Now the Pi Pico can only do 12 milliamps. A red LED has a 1.9 volt drop across it, so to limit the current to 20 milliamps, if this is 3.3 volts, I need 120 ohms to limit the current to 12 milliamps. For an 8 ohm speaker, if this is 3.3 volts, I need 267 ohms to limit the current to 12 milliamps. Those are on the outputs. On the inputs, I want to read these push buttons. Now, this schematic corresponds to this circuit. Once I get the hardware set up, I want to get software set up. Now, the software on a Raspberry Pi Pico, if you want to run Python, that I recommend, run Thonny. Now, there's several languages, assembly, C, Python. Python is really friendly. If you know MATLAB, you basically know Python. The first step is install Thonny on your computer. So locate Thonny 4.14, that's the current version, or whatever the current version is. Download it to your PC, connect the Pi Pico to your board. For example here, I'm running Thonny. Click on the lower right corner down here, and this tells you your board. If you just connect your Pico for the first time, it's going to ask you to download Python. Click yes. Once it's there, I can then connect to it. I'm now connected to my Raspberry Pi Pico. Now, in Thonny, you've got 2 different windows. You've got command window and the shell window. Back over here, command window, shell window. The shell window looks very much like MATLAB. I can say A equals 2, B equals 3, C is A plus B. It looks like a calculator. So I can do operations in the shell window just like MATLAB. In the script window, top one up here, I can input programs. So this is like the the script window in MATLAB. When I hit run, it executes this program and says the result is 17. Change the program. B is now 6. C is now 26. So again, if you're familiar with MATLAB, you're kind of familiar with Python. If you want a lot more information on Python, there's many places you can go. A good place to go is on Bison Academy. Go to 476. This is NDSU's course on advanced embedded systems, basically using Raspberry Pi Pico with Thani. And here kind of walks you through doing binary inputs, binary outputs, analog I/O, motors, sample code, lots of sample code, timers using sensors, temperature, current, heart, pressure, humidity, acceleration, light, motor speed, GPS, neopixels, Bluetooth, Wi-Fi, whole bunch of different examples. Also plenty of websites. So that's kind of the basics of Python. Next, let's get some binary inputs and outputs. So Python is a little bit different than MATLAB. In Python, there's a bunch of different libraries you can use. The libraries have pre-written routines, like machine incorporates the binary I/O functions. To include those, I use the command import. This says import library machine. I now have access to all those libraries. And Thani, you can actually do that. Down here, I can say import machine. What are all the functions available in machine? And again, for more details, please refer to Advanced Embedded. Two of the basic ones are inputs and outputs. To make a pin input, I use the import machine, then say machine.pin of 0 pin out. What this does, this says pin number 0, that's GP0, is an output pin. For inputs, I say machine.pin 6, pin in. It says pin number 6 is input. Pin number 7 is also input, but it's got a pull-up resistor. Pin number 8 is also input. It has a pull-down resistor. So those are the basic commands for inputs and outputs, setting them up. The syntax on Python, what it does is this says use the subroutine pin within library machine. The reason they do that is if I had a second library that also had the subroutine pin, there would not be a conflict. This says this is the pin subroutine within library machine. If there's a pin function within some other library, you specify which one it is. Now, in terms of the inputs, you've got three choices. I can have no resistor, pull up, and pull down. Kind of the assumption is that no resistor means I've got somebody else driving this pin. I've got to drive it at 3.3 volts for logic 1, 0 volts for logic 0. What the pull up and pull down resistors do is they're really designed for things like push buttons. A pull up resistor says the default is logic 1. If I want this to read a push button, what I'll do is I'll take the push button tied to ground through the push button. So when the push button is not pushed, I read 3.3 volts, logic 1. When I push the button, I ground it, I read logic 0. I can also have a pull down resistor. In that case, the assumption is I've got the push button connecting to logic 1. When I push the button, I'm connected to logic 1. When I release the button, it's tied to ground. Now the preferred version is a pull-up resistor. That's because logic 1 is 3.3 volts. If you make a mistake and make that 5 volts or 12 volts, when I push the button, I fry the Pico. So it's safer to use a pull-up resistor and tie the buttons to ground. So this one's actually preferred. But on paper, either one works. That's the binary inputs. For binary outputs, I can read a binary output by doing button.value. This says call the subroutine value associated with button. That'll return a 1 or a 0. Or I can write to the button. To the output. I can do toggle it, set, and clear, and a different way to clear a set. And to kind of illustrate that, let's do some sample code kind of showing how this works. The machine library has the function pin that lets you set things as input or output. The time library has time functions like sleep. Now, another way to do import is from machine import pin. That just means I don't have to do machine.pin everywhere. I can just say pin. A little more convenient. Also assumes there's not a conflict. I can't have the same subroutine name twice. But assuming there's no conflict, this works. I'm going to import pin and sleep milliseconds. Make pin 15 binary input with a pull-up resistor. Pin 16 a binary input with a pull-up resistor. Those are my push buttons. And I'm going to display whether the buttons are pushed or not. It's going to have a while loop. I'm going to keep on looping forever and ever. I'll read the button values, print them, wait a half second, then repeat. So trying it, here's my script window. When I execute it, it's now displaying the push buttons. And notice when the buttons aren't pushed, they're pulled high. That's the pull-up resistor. When I press the first button, that shows up as a 0. Press the second button, it shows up as a 0. That's reading binary inputs. With the time library, I can also do things like have a light turn on and off for 2 seconds. So here the LED is connected to pin 17 through a resistor. I make that pin output, so when I turn it on, the LED turns on, value 0, turns it off. What that looks like in Thonny is to run the program. Light turns on for 2 seconds, then turns off. Let's try it again. Light turns on for 2 seconds, then turns off. In Thonny, or Python, you have for loops, while loops, if statements. A for loop is anything within a for loop has a syntax that for I in range of 0 to 6, this will count 0 through 5. It stops at 6. A little different than MATLAB. The indentation is important. The indentation tells you what's inside that for loop. And here kind of got a character turn. That's actually over here. This is the nested for loop. This goes the first for loop. Here's the second for loop within the for loop. The indentation says this for loop is within the first for loop. If I bring this out, when I remove the indentation, I end the for loop. So in Python, indentations are important. As opposed to MATLAB, they're decorative. A while loop that says as long as t is less than 5, do the following. These are indented. That's within the while loop. There's also if, else if, and else statements. For example, let's turn on and off a light. What I want is GP15 turns on the light, GP14 turns off the light, and GP17 is my light, connected through a resistor to limit the current to 12 milliamps. The way the program works is this. I first define button 0 and 1 to be inputs, the LED to be output. The speaker is left over from some other program. It's connected. I'm not using it currently. Then my while loop. Notice the indentation tells you all this is inside the while loop. I'm going to read button 0, button 1. If button 0 is pressed, 0 is pressed with a pull-up resistor. I turn on the light. If 1 is pressed, Y is pressed, turn off the light. Then print X, Y, and the LED value, the status of the LED, wait 100 milliseconds, then repeat. So here's what that program looks like. When I run it, I can see there's your X, Y, LED is turned off. Hit this button, that turns it off. This button turns it on. Once I turn it on, it stays on. Turn off. When I turn it off, it stays off. On, off. A couple things to note. Indentation is important. If I do something like this, it's going to give me an error message saying the indentation is nonsense, it doesn't know what's going on. If I change the indentation, it thinks this is another loop. Not valid. I got to be consistent with the indentation. And you have to have something inside the if statement. If I don't want anything in there, I can just do pass. Pass is kind of like a no-op statement. Doesn't do anything, but if there's no other statements, at least have something inside the if statement. And I can see that bigger. Let's run this program. There's light on, light off, light on, light off. Stop the program. Next example, let's build a 2-key piano. So what I want is I want to play two different notes, 220 Hz and 260 Hz. To do that, that's the command PWM from Library Machine. To get this to play a square wave, I am going to set up the buttons just like before, LED just like before. But now I've got a speaker tied to pin 14. That's going to be a PWM output, meaning a square wave. The frequency is 220 Hz, and the duty cycle is 0%. Speaker's off. Forever and ever now, I'm going to check. If I hit button 0, I'll play 220 Hz. If I hit button 1, play 260 Hz. Otherwise, turn off the speaker. And to turn it on, I'm using the duty U16. This sets the duty cycle. 0 is 0%, FFFF is 100%, and anything in the middle, like half of that, is 50%. I could also do nanoseconds. This is the pulse width in nanoseconds. So what this program does, so here's the program, and kind of notice the indentation is important. That tells you what's inside the loops. This is inside the first if statement, inside the second if statement, inside the else statement. If I do this, now the sleep's inside the else statement, and there's nothing inside the while statement. Coming down, now this is outside the if loop and part of the while statement. What that does is the program is now running. I have to stop this. All right, where was I? So run this program. Here's what it looks like. You can hear the notes. 260 Hz, 220 Hz, 260 Hz. Now, one way to debug your program, let's pause this, let's throw in a print statement. What the print statement does is it tells you what's happening in the program. So as I run it, currently the speaker is off due to cycle 0. Now it's 220 Hz, 260 Hz. Print statements are kind of nice for debugging. They kind of slow down the program, might mess you up a little bit. Once you've debugged your program, get it working, take out the if statements. I have a 2-key piano. For loops in Python. A for loop is similar to MATLAB's for statement. You can say for I in range of 0 to 5. That'll count 0 to 4. It actually stops when you're equal to 5. Versus MATLAB, it stops when you're greater than 5. So if I do a range of 0 to 5, it just counts 0 through 4, steps of 1. If I do 0, 5, 2, it starts at 0, steps of 2, stops when you're equal to or greater than 5. I can also do an array. This says, take the first element in the array, 1, then 3, then 5, then 7. That's a for loop. I can do a counter. Let's count how many times the button's pushed. What this does is, when I push the button, the signal goes low. So while I push the button, initially I'm waiting right here, waiting for the button to be pushed. When I push the button, it goes low, and I count. When I come back, I then wait for the button to get released. I wait for the button to get pushed, then I count. This is also an example of the pass statement. I have to have something inside the while loop for it to work. In Thonny, I can see that. So going into Thonny, I run the program. This is counting how many times I push the button. I'm getting double counts bouncing on the button. I can try to avoid that by throwing in a pause. 10 millisecond pause. See if that picks up the bouncing. I have a counter. I can return numbers. Correction. In Python, I have subroutines. A subroutine is defined by the words definition. For example, if I have a subroutine right here, defined as say hello, whenever I call it, it's going to print out the words hello. So if I run that, I get the word hello. I can also then call it from the command window. I can pass parameters to a subroutine. Here's a subroutine called multiply. I pass it two parameters, a times b. Let's say, what is multiply of 4 and 6? I get 24. I can then call that from the command window. What is multiply of 8 and 7? I get 56. I can return numbers from subroutines. I can return no numbers, one number, multiple numbers. For multiple numbers, throw it in brackets, and then when I call it, I get back a matrix of 4 numbers. I can call it from the command window. If I return a single variable, that's the matrix. If I return 4 parameters, each one separate. So I can return the numbers separately or together. Finally, if you want something to run on startup, here's how you do that. Take the program that you want. For example, I just want to blink 3 times on startup. The LED is the LED in the upper right corner of your Pico board. And to see that work, this is what that does. So trying that again. Let's make this bigger. If you look at the LED right here, you can see that running on the program. There it goes, blink, blink, blink. Let's make that run on Power Up. So to do that, I go into Thonny and do File, Save As. Now I save it to the Raspberry Pi Pico and save it as main.py. So now what that does, I'm going to power off, unplug the Pico, plug it back in. On Power Up, it ran that program. I just have to make sure that you save it as main.py on the Raspberry Pi Pico. For more information, a couple places to go. One is 476 Advanced Embedded. That's got a lot of information on the Raspberry Pi Pico. We'll probably use that more when you get to Design 2, Design 3. You can also go to W3 Schools, MicroPython Library. Fredscape is pretty useful too. Various places you can go. So that's kind of some background on the Raspberry Pi Pico. In terms of homework set number 3, homework set number 3 is to fill in section 2 on your OneNote document. That's the engineering requirements and Gantt chart. Part of the engineering requirements are that your circuit must operate up to 5 volts DC, have at least one integrated circuit, must have at least one LED running at 20 milliamps plus minus 5, at least one NPN and one PNP transistor. The power supply needs to be 9 volts. You need to use a 7805 voltage regulator to drop the 9 volts down to 5 volts. Have a reverse polarity production diode. We'll talk about that next week. Have a 1/4 watt 1 ohm resistor in series as your current sensor. Update section 3 in your OneNote document to include your circuit schematics, your calculations for RNC, and calculations for voltages. And note that if you're using a microprocessor, assume the output pins are either 0 volts or 3.3 volts. So that's lecture number 3, or week number 3, for Senior Design 1.